Here we're going to look at 4 of the surprising probability problems, the first 3 of which are essential to understand for GCSE maths. The last one is a very unusual problem which is designed to be confusing, but hopefully by seeing it you will learn something about the way probability works and basically learn not to try and guess the answers to things, because often in these questions not quite as simple as they seem. So we'll start with the first one. This is a Venn diagram question where you're given information about 2 sets of people. Some people studying French, some people studying Spanish, and you've got to answer a question about how many students are just studying French but not in Spanish. It doesn't say in this question, draw a Venn diagram, but as soon as you see that there's 2 groups and that there's a potential overlap between the 2 groups, that is people studying both, a Venn diagram should come to mind. So if we start by drawing 2 rough circles like that, and we'll do the box around the edge as well. That is important, that's part of the diagram. We'll label the left hand side one French and the right hand side one Spanish. The problem with this question you'll see straight away is it says 60% said they took French. Now, very common mistake, which I'm sure none of you are making now, is to put 60 in here and then try and add something else in the intersection and realise that the whole circle doesn't add up to 60 anymore. 60% studying French means the full circle, and these are called sets in maths, and that just means group. The full set needs to be 60, but that's going to include the intersection. Same is true for the 30% who are doing Spanish. It would be wrong to put 30% there. Good bit of advice for these questions is start in the intersection if at all possible. The genes question that follows this one, that does give you the central intersection, and if you start there and work outwards, you'll get the right answer. In this question, unfortunately, we're not actually given the number of students who study French and Spanish, so we can't actually start with intersection, at least not just yet. It does say that 20% did not enroll in any language course, so that's another one that you can actually put in straight away. So 20 can go on the outside, nothing's going to interfere with that, that's definitely going to be 20. How many go in the intersection? Well, what is the meaning of intersection? It's the overlap between the 2 groups. If you had everyone in the school and you counted up how many studied French and you got 60%, and you counted again and you counted for how many studied Spanish and you got 30%, you will have counted some people twice, because there's some people that do both. So the intersection is the number of people who are counted twice, because they're in both groups. If we add these 3 percentages up, if we do 60 plus 30 plus 20, you'll see it makes 110. Now you can't have 110% of the school in the diagram. That doesn't make any sense. That means there's 10% extra come from somewhere else. It's meant to be just the whole school. So clearly, 10% of people have been counted twice. That's why it goes over 100 by 10. That means that's what goes in the intersection. So the surplus that's counted twice goes into there. Now we know that 10% are in the intersection, 60% are meant to be in the French in total, so the whole circle makes 60, therefore just 50 goes there. Same for the Spanish, 20 goes there, and that's the diagram complete. How many students, or what is the probability of the student enrolled in the French course but not the Spanish course? Well, that's this number here, 50%. That's why the answer is given here as 0.5. 50% is fine. Okay, so that's a Venn diagram question that's not quite as obvious as some other ones. Here's a tree diagram question that is also not very obvious. It's the question with the 2 boxes and then the red and the white balls. Now this is very similar to the question I showed you with the bowls and the knives and forks. It's basically the same question, just with some boxes and some balls instead. As I mentioned in that video, do not try and guess the probability. Don't try and intuit it. It's not an obvious question at all. It says you choose one box, you choose a ball, you choose a white ball. What's the chance you chose box A? If you try and guess this, you might go, well, maybe it's 1 out of 3 because 1/3 of the white balls are in there. It's not right. You might say it's 3 out of 8 because there's 3 white balls out of a total of 8 balls. Again, not right. You might say that maybe it's a half times a third because there's a half chance of this and then there's a third chance of that. Well, it's a bit closer because at least you're doing combined events, but it's still nowhere near the right answer. It's really hard to get to this correct final answer of 5/11 without properly calculating this with a tree diagram. So it's a tree diagram because two choices are being made. The first choice is the box. The second choice is, once you've chosen the box, which ball do you pick? So we can model it with a tree diagram. First choice is box A or box B. Pretty straightforward. There's a half chance of either of those. So far, so good. Tree diagram is important here because depending on the box you chose, the next set of probabilities are going to be different. It's a conditional probability problem. They're not independent choices. It is going to be red and white in each case, but not with the same probability. So choose box A, you've got a 2 out of 3 chance of getting red there, and a 1 out of 3 chance of getting white. Choose box B, you've got a 3 out of 5 chance of getting red, and then you've got a 2 out of 5 chance of getting white. With these questions, as I've said before, I would highly recommend working out all of the probabilities here. This is a good check to make sure you've done the diagram properly. It doesn't take very long. So A and red, times those two together, remember times the top, times the bottom, you're going to get 2 6. I won't simplify it just yet. A and Y, that's going to be 1 6, half times 3/5 there, that's 3/10, so that's blue and red, sorry, box B and red, and then box B and white, those two times together, so that's 2/10. Even with talking through that, it took about 10 seconds, so just go ahead and do those. Just to check it, these should all add up to 1, because you've covered every single possibility, so everything should add up to 1, because something's going to happen, so there's a 100% chance of something happening. Adding these together is a little bit tricky because they've got different denominators. Quick trick though, these two here, 2 6 1 6, that makes 3 6 as a half. 3/10 2/10, that makes 5/10, it's another half. A half plus a half is a whole, so it works. That makes sense, doesn't it? Because these two came off box A and these two came off box B, and there was initially a half and half chance of those two boxes, so it makes sense that those two would make a half, and so would those. So the diagram looks like it's right. This is the bit that people are confused about, I think. It says that the ball is white. Now, on a GCSE question, you'll typically see that written using the phrase, I'll put it up here actually, given that. So we're given that the ball is white. That means the ball is white. There is no possibility at all of the ball being red. It's guaranteed to be white. You know, you've heard the phrase, it's a given. It's a given that this team's going to win the game. That's a mathematical phrase. It means it's guaranteed to happen. So once you've been given that the ball is white, you can cross out as impossible any outcome that results in a red ball. We're only allowed to deal with these two outcomes now because the ball was white. From here, we're trying to find the probability that we actually chose box A. So it's going to be this one out of the total probabilities that could happen. So that involves a couple of weird fraction in fraction things. So I'll write it out. It's not as confusing as it looks though, if we just talk it through carefully. So this is the thing that we're interested in happening, the box A, and that's got a 1 out of 6 chance of happening. That is out of everything, out of all the possibilities. Like when you roll a die and you say, what's the chance of getting a 4? There's 1 4 out of 6 possibilities. Right, well, there's this 1/6 probability out of these two added together. So you get 1/6 again on the bottom, and then you get 2/10 here. That's our answer. If you're on a calculator paper, you've got a calculator in front of you, you type it in like that, it gives you the answer, that's fine. If you haven't got that, we've got to do a little bit of fraction maths here, but it's not too complicated. So I'll just simplify this one straight away into 1/5, and I'm going to just add the fractions here in the denominator separately. So we're doing that. Pretty straightforward. You multiply these two by 5, these two by 6 to get common denominators. 5 over 30, 6 over 30, add together, 11 over 30. So that is the result of adding these two together. Let's write the fraction out again then. 1 over 6 over, it's now 11 over 30. And with this line here, this over, it means divide. So this is actually the same thing as saying 1 over 6 divided by 11 over 30. Means the same thing. Dividing by a fraction, you do that by multiplying by its reciprocal. So you stick with the first one, you kiss, turn into times, you flip, you make it reciprocal. Because multiplying by the reciprocal is the same as dividing by the original, because they're inverses of each other. So we get this. Not too difficult, this one. You can just work it out as usual. A nice little trick, remember, though, is you can cross simplify. We can divide the top and bottom by 6 in this case. Doesn't matter they're in different fractions because they're going to mix together in the end. I won't do that in this case just because it's not going to help a huge amount. 1 times 30, 6 times 11, and actually now I'm going to divide by 6 in both top and bottom, and I'm going to get 5 over 11, which is the right answer. Okay, that's a really key one to understand. So again, do ask if anything there isn't clear. Now, these last two are deliberately quite strange. The last one especially. Deceptively simple, but in fact, not at all. So the first one, a family has 2 children and at least one of them is a boy. What is the probability that both the children are boys? And you can assume the probability of any child being born a boy or girl is a half. Interesting side note, if you want to research what the probability of getting a boy or a girl in real life actually is, it's pretty close to a half, but it's not quite. And you might be surprised by which of the sexes is more likely to be born. I know I was when I found that out. Anyway, we could do this as a tree diagram because it is 2 events. It's the first child being born and then the second child being born. I will sketch that out, but you'll see perhaps quite quickly why this isn't really a very good way of doing it. A tree diagram, although it will work, kind of is a waste of time in this case. Let me just sketch it out to show you why I think that. So first child, boy, girl, and then the second child, boy, girl, and then here as well, depending on what happened in the first instance. But because they're all halves, it's a pretty boring tree diagram, really. And we'll put them all in here. But you'll see, because there's an equal chance of every single outcome happening, and the chances in the second branch don't change based on what happened in the first branch, you just get a quarter as every single outcome. Now, you can do the same kind of maths that we used before. We can say, okay, at least one is a boy, so therefore it's the same thing as given that one is a boy. We can cross out this girl-girl situation here. And now we're saying, what's the chance that both are boys? Well, it's this one here, this boy-boy. That's our numerator. So 1/4 out of the total possibilities. So 1/4 plus 1/4 plus 1/4. And maybe you can see it's one thing out of 3 of the same thing. It's going to become 1/3 either way. You could work that out in the same way, but it's going to be a third. The reason the tree diagram isn't great here is because they're all equal probabilities. Unlike this last one, where things change depending on what happened in the first instance, this one doesn't. So we're actually just as good listing out the probabilities in a list because they're all the same chance of happening, so we can just pick out the one we want. So I'll show you what I mean. We could get boy-boy, we could get boy then girl, could get girl then boy, or we could get girl then girl. There's 4 chances. Just like you can see here, there is 4 things that can happen, and they're all equally likely. So the list does the same job. It's like rolling a 4-sided die, and you've got an equal chance of each one. So given that at least one's a boy, well, again, we're going to cross out the thing that's not going to happen. So we're going to cross that out. We're left with 3 things. Out of these 3, how many of them are boy and boy? 1. So the chance of getting boy and boy is 1/3. So that's not the weird one. That hopefully makes sense. What's weird is that this problem looks to be almost exactly the same, but as you can see already here, the answer is not. So the family again, they have 2 children. Given that at least one of the children is a boy who was born on Tuesday, what's the probability that both children are boys? Now, why would it make any difference that the boy who was in this first question, it could even be the same boy, couldn't it? I mean, this guy might have been born on Tuesday. It just didn't say. But now that we know he was born on a Tuesday, for some reason that changes the probability that the other child is also a boy. Why would it make any difference that the first one or the second one is born on a Tuesday? Why would that change the probability that they're both boys? Well, at first, it doesn't make any sense. At least I don't think it does, intuitively. But the reason the answer is different is because we've been given different information. When we start listing out the probabilities of this situation, we'll see that it isn't as simple as just 4 combinations. There's lots of combinations now because we've got the extra information. And when we do our crossing out step, we're going to be crossing out a very different number of combinations because we've been limited in a very different way. We're not just being limited 1 out of the 4 combinations here. We're being limited to one of the days of the week. And that's a very different number. So you'll see what I mean when I show you a table of all the possibilities. I'm not going to write everything out because it is very, very large and unwieldy, but I'll do like a kind of sketch of the next best thing. So a table of all the possibilities would, across the top, have the first child, and that would be a child that could be born on Monday, Tuesday, Wednesday, put Thursday there, Friday, Saturday and Sunday. And these are all the boys. Let's put a line there, I think. And then the girl is obviously the same combinations of days of the week. So this is just my shorthand for representing all the different combinations of the first child. So this one here is the first child. We'll call them child 1. I'm not going to actually put these in the table, so I'm not even going to bother using a ruler. It's just a sketch to show you what it would look like. And again, this is a pretty useful thing to do. You have to actually write all these out to get the idea. Child 2 is going to go down here, and it's the same deal here. You got all the days of the week. And that's the boys. Let's do that as well. And then same here for the girls. Now, if you did actually write out all the combinations of boy, girl, and days of the week, I mean, that's very impressive. You will have written out quite a lot. I'm not going to bother to do that. But if I was going to, in each part of this, there'd be a different combination. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then another 14 here, another 14 here, another 14 here. Actually, the number of combinations is 14 by 14. So that, and we need to know 14 squared, 196. There's 196 different combinations of child now, not just 4, because we've got different information about those children. Okay, let's do the crossing out step now. So we are doing the same thing as this. It's just we've got new information now, but it's the same idea. Before we had to cross out any that were 2 girls. Okay, now this one, we're going to cross out anything that isn't a boy born on Tuesday, because that's what's been given. At least one of the children was a boy born on Tuesday. So anything that doesn't have that in it isn't allowed. So rather than crossing out, because there's a lot of crossing out, I'm just going to highlight what we are actually allowed to use now. So it could be anything in this column, couldn't it? Because these are all Tuesday boys here, and anything in this row. So the red is what we're allowed to have. All of these have a boy Tuesday, and so do these. That's our new denominator, but how many is in there? Well, we count across here, this row, there's going to be 14. Boy Tuesday, boy Monday, boy Tuesday, boy Tuesday, boy Tuesday, boy Wednesday, and so on and so on. There's 14 combinations there with this boy Tuesday. Okay, that's a good start. Now down here there's also 14, but the mistake can come in here. We'd end up counting this combination twice. Boy Tuesday is just one outcome. And you wouldn't count it there, here, and you wouldn't count it there again. Kind of like the Venn diagram situation, there's an overlap here. So actually there's only 13 new combinations going down here if we've already counted all 14 across here. We're not going to count that one twice. So it's 14 plus 13. Our denominator, therefore, is 27. It's out of 27. Everything that I've not highlighted in red is now not allowed because it doesn't have a boy Tuesday. Like we can't pick this one because it's got boy Saturday and girl Wednesday. It's not allowed. We're meant to have at least one boy born on Tuesday. It says, what's the probability that both children are boys? Right, well, out of all these things on the red line, these 27 that were allowed, how many of those have two boys? Well, it's just everything in here, isn't it? It's everything in this kind of box here. So if I guess I re-highlight all of that there, just remember not to count this one twice. How many's there? Well, 7 across there, and then a further 6 there. 7 plus 6, it's 13. So there's 13 combinations that have two boys. Out of the 27 we're allowed to pick, because they've got boy Tuesday, that's the answer. So yeah, not so obvious, but hopefully that makes some sense. Do ask if you're not sure, especially about this one and this one. These two are really crucial. This last one, it's just weird, but hopefully it makes sense.